So my name is James Weaver, work for Pivotal. There's my coordinates. I tweet at javafexpert.com. I have a musical blog at culturedear.com. So just reach out anytime. As far as tweeting, I don't know if you're on Twitter at all, or can get to twitter.com/javafexpert. I've tweeted a link to these slides. So they're online. They're kind of live. They've got lots of resources in them that I'll be showing and using. So I would recommend doing that actually, maybe after the session. If you have any questions during the session, I would highly like you to ask them. That'll help me gauge where you're at and what you would like to hear about. As I mentioned, I'm a developer advocate with Pivotal. I've written several books, mostly on Java, Java EE, Java FX. Most recent one is Java and Raspberry Pi. And so Pivotal, our mission is to transform how the world builds software. It's all about digital transformation. We're the makers of, the main contributors to Spring. We have this cloud platform called Pivotal Cloud Foundry. We have in San Francisco and worldwide, we have Pivotal Labs in which we engage with customers and pair program with them, helping them with agile processes and getting their applications done. And then the new kid on the block is production grade Kubernetes, Pivotal Container Services. So we have some cool technologies, but my favorite thing about working for Pivotal is our principles and practices, and my favorite one of those is be kind over there on the right. And so it's, you don't have to tell me to be kind. I feel like I'm a kind person, but it's refreshing to work for a company who one of their prime directives is to be kind. And God knows in today's environment, we need to be kind to each other and treat each other the way we want to be treated. So what we're going to talk about today is quantum computing at an Erlang conference, right? And so I'm going to give you an introduction. And so in order to understand quantum computing, though, you have to understand quantum mechanics. And so we're going to introduce quantum mechanics with Grumpy Cat. So try to make it a little bit fun and palatable. And then we'll get into what you've typically heard about with quantum computing, and that is qubits and some more stuff, quantum computing circuits and algorithms. And then we'll have a hard stop, 45 minutes into the talk, and wherever we end up, that's where we'll stop. So back in the 1940s, I wasn't around in the 1940s, but computers would take whole rooms, and there were a limited number of bits, limited storage. As a matter of fact, people used to take ferrite rings, and connect them with wire, and each one of those rings was a bit, right? So it was very, very limited bits. And everything was brand new. We were just making stuff up back then. And so now, with quantum computing, we're repeating ourselves, where there's massive hardware, takes large rooms. That's a dilution refrigerator that gets down to almost absolute zero. And there's limited qubits. One of the state of the art right now is maybe 20 qubits, and everything is brand new. The software is in its infancy. We're just making stuff up right now, and so here's some proof of concepts in quantum computing. There's the Delft University of Technology, where you've got some students, with some guidance, I'm sure, making a quantum computer. It happens to be using a technology called topological qubits that in conjunction with, I think, Microsoft and Intel, and so they're inventing that. Then over there at the University of Sussex, they're using, for their qubits, this technology called trapped ions. And so they're having fun over there doing that. There's the professor that's the lead of that project. And so then you might ask, well, why quantum computing? Why use a quantum computer? And the answer is, well, there are a couple of answers. One is because it's there, right? And so we have quantum mechanics that kind of rules the universe, so why not leverage it for computing? But but as far as like practically, why use it? Well, there are some solutions to problems. That's the universe of this Venn diagram. Some solutions are feasible on classical computers, and some are feasible on quantum computers. Some, it's very expedient to do it either way. But there's some problems over there that are only feasible on quantum computers. It'll never be feasible on a classical computer. And so some of those, so another driving factor is that transistors can't get much smaller. So there's an effect called quantum tunneling, to where a piece in a transistor, a part of a transistor, the electron, rather than being blocked like when it needs to be blocked in a transistor, actually tunnels through. Right? You have this effect called quantum tunneling. So one answer to that is make your materials so that they can't tunnel, and then another answer is embrace the quantum effects, right? And so that's another driving factor. So what are some of the problems that you're not going to be able to do classically? Well, one such problem is factoring large numbers. Factoring large number is something with a high order of complexity, and so with Shor, with RSA cryptography, for example, you might have a 400-digit number, and it was created by multiplying two prime numbers. So multiplying two prime numbers is easy, but factoring a 400-digit number into two prime numbers is very hard. It could take hundreds of years, classically. But this gentleman by the name of Dr. Peter Shor, back in 1994, created an algorithm that takes a part of that process for factoring large numbers, it's called period finding. And he took part of that and applied a quantum computing algorithm to it, and proved that we can do it exponentially faster by using this algorithm. And so that's one of the driving factors for why it started to become very attractive to push forward in quantum computing. And then here's a paper at the bottom that has a link there that's a very approachable paper that talks. It's by Dr. Shor that talks about that. So then the next year, Dr. Love Grover over in India, he created this algorithm for finding a record in unsorted data. And so, if you have lots of data, and you're trying to find one record in unsorted data, that's like finding a needle in a haystack. And so he created a quantum algorithm that would do that. And so that's another kind of driving factor. There's a nice paper. And I like his quote here. He says, "Programming a quantum computer is particularly interesting since there are multiple things happening at the same time, simultaneously. You need to think both like a theoretical physicist and a computer scientist. So you have one foot in both worlds, computer science and understanding quantum mechanics." And some of you may recognize this gentleman, Dr. Richard Feynman, over on the left. And anybody watch Big Bang Theory at all? Anybody like Big Bang Theory? Right, so Sheldon, sometimes he'll play the bongo drums. Well, Dr. Feynman used to play the bongo drums. And so anytime Sheldon's playing the bongo drums, it's kind of an homage to Dr. Feynman. So Dr. Feynman was one of the pioneers in quantum mechanics. And I love this quote. It says, "Nature isn't classical. And if you want to make a simulation of nature, you'd better make it quantum mechanical. And by golly, it's a wonderful problem because it doesn't look so easy." So what he's talking about there is that, let's say that you're trying to model chemical reactions, or anything in nature really. For every additional particle that you're trying to put into the computation, you've just added a bit. Well, if you have, 2 to the 100th, if you have 100 bits, what's 2 to the 100th power? You start to run out of, you start to have more possibilities than you do, atoms in the universe kind of thing, right? So binary and, so the whole classical bits and having that being your underlying calculation storage starts to run out when you talk about modeling real processes like chemical and real quantum processes like our world is made up of. And so he said, it's not classical, and if you want to simulate the nature, you better make it quantum mechanically. So he kind of challenged the world to create quantum computers, is what he did there. And so now we're beginning to leverage it for quantum computing for chemistry. Over on the left, there's a nice Nature article about that. Over on the right, there's an archive paper about Open Fermion, which is a library that's Google and others are sponsoring for being able to have a developer like you and me that aren't PhD physicists or quantum computing experts or whatever, and be able to use this library then for being able to model chemical processes, applying quantum computing algorithms to them. Another couple of archive papers, these actually were written by some researchers in China. This one over on the left is ground to satellite quantum teleportation. So the idea of being able to, what they were trying to do is prove this idea of entanglement and using it for communication. What they did is they took two photons, two particles of light, they entangled them, and then they shot one of them up to a satellite. And then they did the classic experiment where you observe one, kind of like the Schrödinger cat experiment. You observe one, and the other one, it collapses into a state, like vertically polarized or horizontally polarized. And you observe the other one that's on the ground, and it is the same state. It collapses to the same state. So exhibiting this law of entanglement. So they did that, and it was a successful thing, and so they proved that even between the ground and a satellite, that it could be instantly proven that it was entangled. And then they did it the other way too, satellite to ground. And so they took it from the satellite, they entangled two photons, shot one down to the ground station, did the same experiment, but in addition what they did is they transmitted a key, just a classic RSA key, just to prove that they could transmit a key over a quantum channel. And the advantage there is that because of collapsing, if you would intercept that transmission, then it would collapse to a state and then become unusable. And so you can tell whether that key's been sniffed or compromised. Another way that it's being used, starting to leverage as far as research, is machine learning. So part of machine learning algorithms are, being like teaching a neural network to learn, to go from inputs to output. Like, for example, seeing a picture of a cat and recognizing that it's a cat versus a dog or something like that. Part of that is training the neurons and the connections between the neurons in a neural network. And the way that's typically done is this technique called gradient descent, where you're trying to take the error out of the network. And so researchers are then, like this PhD student here, are looking at quantum techniques, quantum algorithms, to be able to do the same kind of thing, to descend gradients. And so that's another use for it. Okay, with that introduction, now we're going to dive into quantum mechanics. But we're going to try to make it friendly. So there's Schrödinger's cat over there. He's Grumpy Cat. It says Schrödinger's cat, Schrödinger liked cat as much as I like humans. And And so we're going to go through the axioms. There are 3 axioms of quantum mechanics. There's Grumpy Cat over on the left. There's a kind of a cartoonish figure of Grumpy Cat on the right. And he's actually, he's within this mathematical notation here that's called a ket. There was a physicist by the name of Paul Dirac that created this notation that allowed physicists to manipulate vectors, just like single dimensional arrays. And to make that easier, he created what's called a ket. And so that's that notation. So I have this cat, very, very small. I can only see him on a microscope. Sometimes my cat is actually happy, and sometimes he's grumpy. I've never observed him between those 2 states. Anytime I observe him, he's either grumpy or happy. And so that leads me to the first axiom of quantum mechanics. It's called the superposition principle. And that is that a particle, any quantum mechanical element, can be in a superposition of 2 states, let's say. In this case, grumpy and happy. And if we look at, this is a unit circle here, and this unit circle represents all the states that my cat can be in quantum mechanically. So I've only observed him either grumpy or happy, but before I observe him, right, before his state collapses, he can be in any one of these states on this unit circle. And so he can be fully grumpy, fully happy. He could be in this superposition, this equal superposition of grumpy and happy, with the associated amplitudes being the x and the y distances. So in this case, the amplitude is 0.707, which is, the square root of 1/2 on the grumpy axis, right? And then the square root of 1/2 on the happy axis. So that's his state equal superposition. And this link right here, by the way, this link down here in this slide is a link to Desmos, where we can have a kind of a simulation here. So here we've got, he's fully grumpy, 1, 0. Here he's fully happy. Here's that superposition between the 2. Notice over here then these numbers. Here's the degree, but over here these are the amplitudes on the x and y axes at 0.707, 0.707, and then these numbers are the square of those numbers. So the square of, on the x-axis, if I take the half of square root of 2, or the square root of 1/2, if I square that, I get 1/2. So that's what we have here, 0.5, and then we have 0.5 here. And what those represent are probabilities that if I observe this cat, that he'll be either grumpy or happy. So if and I'll get into measurement soon, but because this number here is 0.5, that means if I observe the cat, there's a 0.5 probability that it'll be grumpy, or a 0.5 probability that it'll be happy. But if he were in this quantum state, for example, then here's the amplitudes, 0.5 on the grumpy axis, 0.866 on the happy axis. If you square those, we get a probability that if we observe the cat, that a probability of 0.25, 1/4, that it'll be grumpy, and 0.75 that it'll be happy. Okay? Any questions so far? Okay. You might wonder then, well, what about the rest of the unit circle? What about over here? let's say right here, where we have minus square root of 1/2 grumpy and minus square root of 1/2 happy, what's the probability that that cat would be happy or grumpy? What is the probability? Somebody tell me. What's the probability that my cat in this state would be grumpy? 1/2, exactly. So because the square of a negative number is a positive number. Okay. So the way that we can represent quantum states is either geometrically here. So this quantum state, by the way, is the one I just showed you a second ago. Here we've got the amplitude on the grumpy axis, the root of 1/3. Amplitude on the happy axis is the root of 2/3. And because of the Pythagorean theorem here, right? The hypotenuse here is the square root of the hypotenuse is the sum of the squares here, right? So square of the root of 1/3 is 1/3. The square of the root of 2/3 is 2/3. You add them together, you get 1, right? So we're representing this quantum state geometrically, but there's another way. There are other ways of representing the quantum state. One way is with vector notation. So a vector is just a one-dimensional array. You can think of it as a one-dimensional array. So over here, the state of grumpy is 1 on the x-axis, that's the top number, and 0 on the y-axis. So the way that you would represent the grumpy cat is 1, 0. The way that you would represent the happy cat would be 0 on the grumpy axis, 1 on the happy axis. Okay, follow me? Any questions on this so far? Okay. And then the way that you would represent this other state that we've represented over here geometrically then is root of 1/3 grumpy, that's that ket notation, root of 2/3 happy, that's in ket notation, and then in vector notation over there then you'd say root of 1/3 for the first element of the vector, root of 2/3 for the second element of the vector. Okay? So that's the superpositional principle and how we can represent that. So now, if there's no questions on the superpositional principle, then now we'll go to the second axiom, which is called unitary evolution. And what that means is that a quantum state can evolve from one state to another with the use of gates. And the way that those gates are represented there is using a very elementary linear algebra. So here we've got a grumpy cat, and then we've got this not gate. And then we've got, you run the grumpy cat through the not gate, and you get a happy cat. The not gate it's called a not gate. It's also called a poly X gate or a bit flip gate. And the way that that's modeled is with a vector. With a matrix. So the X gate is actually modeled with a matrix here, this matrix. And as we know, the grumpy cat can be modeled with that vector, right? 1 on the grumpy axis, 0 on the happy axis. And if we do the multiplication here, if we multiply this vector by that matrix, or the other way around, matrix by the vector, then we would get 0, 1. And there's a trick when you've got a vector with just 1s and 0s in it. Here we just pick out the first column because the first row is 1 here, so we'll just pick out the first column, and that's what goes over there. So taking the grumpy cat, multiplying it by this not gate in terms of the matrix, then we get the happy cat. So all of the unitary evolutions in quantum mechanics it's kind of cool that it can be expressed as simple linear algebra. So it takes a lot of the the mystery out of it. You can model this with linear algebra. Okay, so here's a slightly more complex gate. It's called a Hadamard gate. And Hadamard gates are great for putting cats in equal superpositions. And so the way that any single qubit gate, or any single cat gate is modeled with a 2x2 matrix there. So this one is a 2x2 matrix of the square root of half here, except for this one is minus there. And so if we took Grumpy Cat, and if we took this, this Hadamard matrix here, that matrix, and multiply it by Grumpy Cat there, we pick out the first column of the matrix, and that's the answer. And so what do we have there? We have this equal superposition of grumpy and happy, which is what we see over in ket notation up there. So taking our grumpy cat through the Hadamard gate puts him in a equal superposition of grumpy and happy. And these equal superpositions it turns out that these are building blocks for a lot of the algorithms that really give a quantum advantage, as you may see later. So that was the second axiom, which is unitary evolution. The third axiom, which I've already kind of talked about a little bit, is called measurement. So the probability that you'll see when you measure some quantum particle or a cat, when observed, is going to be the square of the amplitude, right? So if we had a cat that was in this superposition of a root of 1/3 grumpy and root of 2/3 happy, then what is the probability, please tell me, what the probability is that when we observe this cat, that the cat will be observed as grumpy? 1/3, very good. And probability of being happy is 2/3, very good. And so now, so that was the three axioms. So now we're going to talk about multiple cats. What if we had more than one cat? So here we have two cats in this ket notation. So we have like two quantum states, right? And so we have this state that is consistent of two cats, and we can factor that and say, okay, well that's the product of the individual quantum states, individual cats. And then remember, grumpy cat is 1, 0, grumpy cat 1, 0. And what we're going to do then, when you have a composite state that's made up of more than one quantum state, then you take what's called the tensor product. And the tensor product is a pretty simple operation where you take each of the elements of this vector and multiply it by each of the elements in this vector. So if we have a vector of 2 elements and another vector of 2 elements, we're going to end up with another vector that has 4 elements in it. So this is how it works. We're going to take the top 2 elements, 1 times 1 equals 1, we're going to put that in a vector over there on the right. And then we'll take 1 times 0 and put that over there, 0 times 1, 0 times 0. So the result of the tensor product of grumpy and grumpy is 1, 0, 0, 0 in this vector, where the first element there, the 0 element of the vector, is grumpy grumpy. There's just a binary progression over there of grumpy grumpy, grumpy happy, happy grumpy, happy happy. And somebody says joy joy that grew up in the 90s, right? So anyway, so now we have multiple cats, maybe grumpy and happy. They're individual now, individual quantum states. Take the tensor product, go through that operation, and we end up with 0, 1, 0, 0, where the 1 is beside this this quantum state of grumpy and happy. Okay? So what if we had 3 cats? I'm not going to go all the way to 100 cats or anything, but I just want to kind of drive the point home. 3 cats, grumpy, happy, happy. Take the tensor product of those 3, and what you end up with is 0, 0, 0, 1. The 1 there is beside that particular quantum state. And it doesn't always have to be 1s and 0s. It can be, 1/3, root of 1/3 and root of 2/3 and things like that that we've talked about. So putting this all together then, as far as like the 3 axioms, superposition, unitary evolution, and measurement, let's just take it through a scenario. We start out in a quantum state of grumpy, grumpy, and we maybe put it through some gates that ends up being in that state where we have root of 1/2 grumpy, happy, plus root of 1/2 happy, grumpy. Just whatever gates it took to put it through that. And let's say we put it through some more quantum gates where that's the result. Right? So we have that particular quantum state, that composite quantum state. So what is the probability that we end up with grumpy, happy? Anyone? When measured. Measure that quantum state, what's the probability that the quantum state will be grumpy cat, happy cat? Oh, sorry? 50%, 1/2, that's right. Measure that one, what do we get? 1/6, and what do we get? 33%, yeah, exactly. Thank you. All right, so that's, any questions on anything we've talked about? You understand the axioms of quantum mechanics. That's kind of cool, actually. Not bad for a half hour, I guess. You giving me 2 high fives? Okay, so I got 10 minutes. So let's talk about quantum entanglement. Who has heard of quantum entanglement besides when I talked about it just a second ago? Okay, so Einstein called this quantum mechanic entanglement spooky actions at a distance. Because like in the satellite thing, right, where you entangle 2 photons and you measure one here, it could be on the other side of the solar system. You measure this one and instantaneously this one collapses to the same state. Well, Einstein didn't like that. Yes?
It depends on the definition. If you think that there is a collapse that happens, then it's spooky action that propagates through the universe. If you use different definitions, there are no collapses and no spooky actions.
Yeah, so over a beer, we're going to get really philosophical later. That's awesome. Yeah, and we're going to talk about multiple universes and things like that, right? Okay, all right. So anyway, so we have Alice cat and Bob cat. And who's heard of Alice and Bob? They've had this long distance relationship for years, I guess. But so there's Alice and Bob. So we run Alice through a Hadamard gate. Remember Hadamard gate? So it puts Alice into an equal superposition of grumpy and happy. Well, Bob didn't run through a gate. He's just still full on grumpy. And then we're going to take another gate called a C-not, a conditional not gate. And a C-not gate is if this is grumpy here, in this case if this is grumpy, then like 1 or something, then this will be flipped, and then it'd be the case where happy, then this gets flipped, grumpy, this doesn't get flipped. And so what we end up with then is this state here where the square root of half, or the half probability, I guess, that you come up with a grumpy, grumpy state, and half probability that there's a happy, happy state, right, when measured. And so what happens is whatever, and that's called, by the way, the Bell state. A guy named John Bell came up with that. So what happens then is if we took Alice and she went on a spaceship to Venus, and then Bob went on a spaceship to Mars, and if we observed Alice, and if Alice were happy, then as soon as we observe Bob, then he would be happy. But if we had have observed, let's say, Bob, and he was grumpy, then Alice is grumpy. And that's this idea of entanglement, or spooky actions at a distance. So, who's heard of Emerson, Lake and Palmer? I really need to know my audience here now. Who has heard of ELP? Okay, so, all right, so there's this rock band called ELP. 1972, they came up with this album called Trilogy, really power trio, really cool. Well, there's this thing in there's this research paper, and actually it spun off. It was actually done by this power trio, the band, in 1935, Einstein, Podolsky, and Rosen, and they called it Paradox, and so there's their profiles there. And some of the songs on the track were Spooky Accident at a Distance, Hidden Variables, Local Realism, God Doesn't Play Dice with the Universe, but they all had to do with this paper that they created. It was called Can Quantum Mechanical Description of Physical Reality Be Considered Complete? So Einstein always had a problem with this idea of entanglement, and one collapsing and then the other collapses. He had two problems with it. One was this idea of spooky actions at a distance, right? Where there seems separated particles, and you measure one and the other one's instantly in the same state. Well, that's the locality problem that he had. And then realism was that a quantum state doesn't collapse or doesn't, isn't decided until you observe it. And he used to say, I like to think that the moon is there even though I don't see it, even though I'm not looking at it. So that's why track 9 on their album was The Moon Exists Even When I'm Not Looking. So anyway, there's a link to that paper. It's actually a very short paper, digestible. But then along comes John Bell in 1964, and he came up with this theorem that says no physical theory of local hidden variables can ever reproduce all of the predictions of quantum mechanics. What he's dealing with, what he's talking about there, is that Einstein always had a problem with this entanglement and local realism, and Einstein thought that there must be hidden variables, these local hidden variables. You entangle two particles, you separate them. There's got to be some hidden variables in these particles to where it's predestined, that when you measure one, that the other one's going to be, collapse to the same state. And, so it's already part of the state, and so of course it's going to collapse to the same state. And so Bell, his theorem is no physical theory of local hidden variables can ever reproduce all the prediction of quantum mechanics. So he was saying, it can't be local. It can't be local hidden variables. And so then these are two really good videos. One is Physics Girl. She calls herself Physics Girl. It's a very approachable video, and it talks about the quantum Bell test. And then this is a researcher in Vienna, where she goes in lots of detail about how they tried to close all these loopholes, all the loopholes that there could be in this test. So anyway, there's also, who's heard of 3 blue, 1 brown? It's, okay, good videos, right? So they did one on quantum mechanics in the context of polarized light. You can take polarized filters and watch, you can literally observe collapse, and measuring instead of grumpy and happy bases, horizontal and vertical bases with polarized light. So on to from cats to qubits, and I'll just kind of introduce this real quick. I've got maybe 3 minutes, I guess. Quantum computers aren't made of cats. Sorry. They're made of they're made of like particles, like you know, electrons or you know, trapped ions or you know, whatever. And with classical bits, computers, you know, the things that are in the computer can represent 0 and 1, right? A circuit being completed, you know, some state of a transistor or whatever, classically. With qubits or with quantum computers, as we just said, you can have superpositions of 0 and 1, of grumpy and happy. And so in quantum computers, the way they represent those is with something called qubits. And those qubits can have a state of either 0 or 1 or some superposition. What this is, remember what we showed you the unit circle, it's actually, not to be scary or anything, but it's actually more accurately represented as a sphere because you also have, like on the equator of the sphere, that's the complex plane in which you can represent phase information, which is really important for quantum algorithms. And so everything I showed you about cats is really true about qubits. You know, it's all the same thing. It's just a lot easier and more fun to introduce with cats. And there's lots less ones and zeros when you try to do it. I'm going to leave you with this. I think I have 1 minute probably. And that, do I have 1 minute even? Okay. All right. So how would you represent qubits in hardware? Well, photons, electrons, like electron could be spin up or spin down. It's not really spinning, but, and then superconductor like energy levels, ground state or excited state. And if you get these slides, what I'd like you to do is go into this Quark simulator, and in that you can then do all sorts of like simulations of circuits, like with Alice and Bob. You remember Alice and Bob, and being able to entangle them. Well, here's Alice, there's Bob. I can run, remember that we had that Hadamard gate. We can put through them a Hadamard gate and then put them through that C0, and that's the same circuit. And the outcome then is either 0, 0, grumpy, grumpy, or 1, 1, happy, happy. And so this is a tool called Quark by Craig Gidney, which is really good for being able to play with quantum circuits. Thank you very much for your attention and participation.